Most analysts prefer a simple formula. The Zuma-class destroyer was an overly expensive experiment, so the next step should be as cautious as possible. Logical, convenient, almost like a risk management handbook. But war at sea rarely follows convenient logic. In the early 2000s, the United States Navy bet not on modernization, but on a break with the past. The Zonal-class destroyer was conceived as elite, minimal signature, new power architecture, radical automation. It was a ship designed not for the current war, but for the next generation of conflict. But strategy changed. Threats evolved, and the price proved too high for serial production. Instead of becoming the backbone of the fleet, it turned into a technological showcase, powerful but singular. And that experience now hangs over the new project as a warning. The DDGX program is emerging in a different atmosphere. It's not an attempt to impress the world with whole shapes or futuristic solutions. It's a search for balance, preserving power margins for lasers and future missiles while creating a platform that can be scaled, modernized, and kept within budget. Today, the question is sharper than it was 20 years ago. The fleet does not need an experiment or assemble. It needs a ship that can survive multiple technological cycles and remain relevant in the era of hypersonic weapons and unmanned systems. Will they manage to combine ambition with calculation this time? That's what will truly determine the future of American destroyers. Let's break it down in today's video. The U.S. Navy enters the second quarter of the 21st century with fleets of very different ages. Ticonderoga-class cruisers are over 40 years old. Many Arleigh Burke-class destroyers are nearing the limits of their service lives. And the three futuristic Zumwalt-class destroyers, while newer, remain technological demonstrators rather than true workhorses of the Navy. The service urgently needs a new hull capable of serving into the 2080s, carrying hypersonic missiles, and providing power for megawatt combat lasers while remaining serially built and, if not cheap, at least economically tolerable for taxpayers. These requirements were formalized in the December 2020 top-level requirements, marking the official start of the next-generation guided missile destroyer program, DDGX. Let's be clear, DDGX did not appear because the Burkes failed. On the contrary, they became such a successful platform that their longevity is precisely what delayed the arrival of a true successor. In 2022, Naval Sea Systems Command NAVC directly called DDG-51 an outstanding success, noting that the class holds the record for the longest production run among U.S. Navy surface combatants, and that the newest Flight 3 ships will remain in service until the 60s. However, let's be realistic. The main limitation of Arleigh Burke is future modernization, which will almost certainly demand additional space, weight margin, and most importantly, energy from already aging hulls. Yes, displacement grew from the original 8,400 tons to 9,900 tons, but the electrical margin on the latest Flight 3 ships has already been largely consumed by the AN Spy-6 radar. Engineers have been forced to install additional generators directly in the superstructure, at the cost of increased noise and more complex cooling. Burke remains a very capable ship, but its architecture was shaped in a different era. With each new modernization phase, it becomes harder for the Navy to integrate heavier and more power-hungry systems into a whole that was not designed for today's electrical and computing demands. That's where the need arises for a new platform designed from the onset with growth margin for advanced sensors, communication systems, missile defense components, electronic warfare, and the most ambitious energy-intensive weapons. If Arleigh Burke is a story of long-term success, Zumwalt is a story of a revolution that came too early. Calling them a failure would be incorrect. These futuristic destroyers showed the Navy what large surface competence of the future should look like in terms of power generation, automation, and growth margin. The issue is that the path to that future proved too abrupt and very expensive. For this reason, in its materials on DDGX, the U.S. Navy has repeatedly emphasized that the new destroyer program will follow an evolutionary rather than revolutionary approach. By 2026, each of the three Zumwalts costs approximately $7.5 billion, including research and development, 3 times the original program estimate. Today, its main pitfalls are clearly visible. The specialized 155mm Advanced Gun Systems, AGS, depended on a single munition, the Long-Range Land Attack Projectile, LRP, whose cost soared to $800,000 per round. Procurement was cancelled in 2016, leaving the ships effectively without ammunition. The shore bombardment concept lost relevance, while missile defense and hypersonic interception required entirely different systems. The complex hull geometry reduced radar cross-section, but worsened seeping and complicated corrosion repair. Lack of growth margin. Although the ships had significant power around 78 megawatts, they did not provide space for a larger vertical launching system VLS or the future railgun the Navy had been developing. All of these missteps became a ready-made checklist for DDGX designers. At minimum, we'll not see exclusive ammunition types again. Instead, we'll almost certainly see a hull with displacement up to 14,500 tons, traditional vertical sides, and far more space for future VLS capacity. If energy density was an end in itself for Zumwalt, for DDGX, it's a tool for the next 50 years of modernization. The Integrated Power System, IPS 2.0, includes two Rolls-Royce MT-30 modular gas turbines rated at 36 megawatt each along with lithium titanate buffer batteries to smooth peak loads from systems like lasers. The plant will be able to provide up to 32 megawatts of free power for sensors and weapons, and a DC distribution bus will allow one module to be taken offline without blacking out the ship. The lesson on modularity was learned during Zumwalt's early operational issues when system failures revealed vulnerabilities. Electric drive will also reduce the acoustic signatures since there are no traditional drive shafts and the motors are mounted on vibration-isolated foundations. Unlike the AGS on Zumwalt, the IPS capacity of DDGX is supported by a weapons roadmap that includes a 150 to 300 kilowatt Surface Navy Laser Weapon System SNLWS Increment 2, formerly known as ALIOS Block 2, a megawatt-class chemical laser and potentially a railgun demonstrator in the mid-2030s, although the latter is currently a system the Navy's officially stepped back from. Cooling deserves special mention. DDGX will use a closed-loop water glycol system, rejecting excess heat through coolers with the option of additional hybrid Freon condensers. This lesson was learned during SPY 6 integration on Arlery Burke, where reinforced chillers and expanded cooling lines were required. As for dimensions, the Navy insists DDGX must be built and serviced in the same docks that currently handle Arlery Burke without exotic infrastructure. Designers will therefore need to fit the ship within roughly 69 feet of beam and about 30 feet of height to match the facilities at Bath Iron Works and Huntington Ingalls Industries. Though Bath Iron Works has discussed widening to 78 feet, the superstructure will consist of large composite panels that can be removed by crane and standard dry docks. Unlike Zumwalt's monolithic composite deckhouse, major components from radar sections to generators will pass through rectangular service hatches roughly the size of a Euro pallet, avoiding hole cutting during upgrades. Crew size of 220 to 240 was chosen as a compromise. Enough automation to reduce cost compared to Burke, but a larger crew than Zumwalt. Combat electronics will be distributed between two isolated mini data centers fore and aft. If one is disabled, the other can retain control of both the ship and its weapons and simplify repairs. Universality will be DDGX's central bet. Instead of multiple AGS guns forward, there will be a VLS XL battery around 40 feet long compared to the Navy's standard 25 feet -41 Malawian Quachar cells. It'll be large enough to carry a single conventional prompt strike CPS hypersonic weapon or a future hypersonic ground launch cruise missile GLCM. With an adapter canister. It could also carry 3 SM-6 missiles in the same cell. 127mm -45 Malawian Quachars Mod 5 gun will remain, and thanks to existing VLAP guided rounds, the ship will not depend on unique munitions. 4A SPY 6 V1 radar panels will provide 360 degrees coverage, and electronic warfare systems will be integrated into the superstructure faces, eliminating the forest of masts and antennas seen on later BKS. Two 300 kilowatts laser systems will provide close-end defense with initial testing plan for the first production hull funded in FY 2031. In the future, VLS XL is expected to host a hypersonic glide phase interceptor, HGPI. The tandem defense concept is that a laser first disrupts the plasma envelope of a hypersonic target, degrading its guidance, followed by a kinetic interceptor to destroy it. Under the Distributed Maritime Operations DMO doctrine, DDGX is envisioned as a floating server not only shooting, but distributing energy computing power and tactical data across the force. With over 30 megawatts of reserve capacity, it could recharge unmanned surface vessels and UAVs. Through Link 22 and the Tactical Targeting Network Technology, TTNT, the destroyer effectively becomes a host node processing sensor feeds from dozens of platforms. Simultaneously, smaller ships, upgraded littoral combat ships, and future large unmanned surface vehicles, LUSV, would shield DDGX from torpedoes and low-speed UAVs, while the destroyers handle early detection, initial interception, and coordination of hypersonic defense. That's why the Navy is not pursuing extreme stealth. Instead of the costly tumble-home hull of Zumwalt, DDGX uses conventional vertical plating combined with active signature management, digital EW modules, controlled reflectors, and decoys. This managed signature approach is far less expensive and easier to upgrade since changing algorithms is easier than reshaping steel. Risks remain. Technological risk. If lasers, HEPI, or a naval railgun are delayed, the ship could slip. Cost growth. If early ships exceed $4 billion each, Congress could reduce or freeze procurement. Political factors. Alternative large surface content concepts could divert funding. Industrial risks. Delays in yard upgrades or MT-30 turbine supply disruptions could push yards back toward continued Flight 3 production. To mitigate risks, the Navy has emphasized transparency. Designs are published through USNI News. Contracts are tied to strict KPIs and budget hearings are highly visible, the opposite of Zumwalt's quiet launch. According to the Congressional Budget Office, under the 2025 shipbuilding plan, DDGX will cost $3.1 to $3.4 billion per ship for 28 hulls through 2055, more than Flight 3's $2.2 billion, but justified by life cycle savings, standardization, and continuous reduction. DDGX is not a bigger berg. It's a calculated blend of steel hull design in the era of energy weapons. It corrects Zumwalt's mistakes and offers what Flight 3 cannot. Free megals for radars, lasers, and hypersonic weapons, plus a digital architecture upgradable at the speed of software. Whether the program maintains its schedule and price target depends on two factors: budget discipline and industrial supply chains. If they hold by the mid-2030s, DDGX could fill the gap between aircraft carriers and light frigates, taking on the heaviest air and missile defense roles and opening a new chapter in American sea power. What do you think? Will the U.S. Navy field these destroyers by the early 2030s, or will it take much longer? Share your opinion in the comments. And if you enjoyed the video, don't forget to like, subscribe, and turn on notifications. See you soon.